We've seen two settings for cryptography, the symmetric setting and the asymmetric or public key setting. And each of those requires something with regard to the keys that parties need to have to be able to engage in the cryptography. And despite the fact that once these keys are established, things work fairly easily and well, the process of managing and establishing the keys can be quite complex and difficult. And this has led cryptographers to continue to be creative with regard to finding settings, perhaps with different kinds of requirements on keys that enable basic cryptography. And one, at this point, the third answer or setting that has been provided and we're going to look at is identity-based cryptography. The idea goes back to Adi Shamir quite a while back, and he introduced it in this paper of which you see a little snapshot here, where he says we introduce a novel type of cryptography, and the idea was that you don't need anything like a public key. The only thing you need to communicate or send a message encrypted to Alice is Alice's email address. Intriguingly, while Adi had the idea of this model, he wasn't able to realize identity-based encryption, and he left it as an open problem. And it wasn't until 20 years later that Boneh-Franklin came up with the first identity-based encryption scheme. And what made this possible was a new kind of number theory brought into cryptography, and that was bilinear maps or pairings. These pairing-based cryptography or bilinear maps have had a huge influence even beyond the possibility of realizing for the first time identity-based encryption. And as you can see here, this has been recognized through awards and lots of publications, and now quite a lot of usage of IBE. So let's step back to see how, or recall how, the public key infrastructure setting works. So here, when Alice wants to send an encrypted message to Bob, she first needs Bob's certificate. From that certificate, she extracts Bob's public key, and then she can perform the encryption, produce a ciphertext which gets sent to the receiver Bob, and using the secret key associated with the public key, Bob can decrypt. In order to provide that certificate, we needed a trusted certificate authority. So the process would begin with Bob contacting the CA, getting a cert, then sending the cert to Alice, and now Alice can start encrypting. Identity-based encryption envisions things differently. The sender, Alice, has no public key for Bob. All it has is Bob's identity. Think of an identity as an email address and or possibly a URL or something different like that. As a function of that and a message, Alice will produce a ciphertext and send it to the receiver Bob. How would Bob decrypt this? Well, for that, a trusted authority is invoked, and that trusted authority can provide Bob with a secret key associated to his identity. So he is bob at example.com, and the secret key is associated to that, and then using that, he can decrypt the ciphertext. So in particular, things begin with Alice. She can send encrypted information without any a priori information received from Bob. And Bob will request a decryption key upon need. There are no certificates here. We'll come back to how these models compare in sort of effectiveness and security, but first let's explore in a little more depth what IBE is and how it might be built. So as with other primitives, we'll give both a syntax and a security definition. The syntax of an IBE scheme prescribes 4 algorithms: parameter generation, key generation, encryption, and decryption. So one more than a usual encryption scheme. Parameter generation is run by the trusted authority, and it generates what's called a master public key with a master secret key. Next, let's look at encryption as run by Alice. This takes the message that she wants to encrypt, and it also takes the identity of the receiver. From the point of view of the formalism of IBE, the identity is just a string. But in usage, you would think of it as perhaps an email address. Now, something we slipped under the rug in the prior picture is that the encryption algorithm also needs this master public key. So you think of this master public key as created once and then broadly disseminated or embedded in a browser or whatever. As a function of those 3 things, the encryption algorithm will create the ciphertext. Now that ciphertext is passed on to decryption, and who needs to figure out how to recover the message. Decryption knows the master public key, of course, but so far, decryption has no secret key. Well, it has to get one. How does it get it? The identity is provided to the trusted authority who runs a key generation algorithm. This uses the master secret key together with the master public key, and based on them derives a decryption key specific to this identity. And then the decryptor here gets that decryption key and can recover the message. Okay, so decryption keys are associated to identities. Different identities will have different ones, but to produce such a decryption key, you need the master secret key over here. Of course, there's a correct decryption requirement, which says that messages encrypted by this algorithm and decrypted under the key corresponding to the identity used here will decrypt correctly. So in a little more detail, let's say that I generate the master public and secret keys, run encryption with the master public key for some identity and message to get a ciphertext. Now I decrypt that. The key I use is the one associated to the identity here, generated using the master secret key. And this says that in that case, I will always recover the same message as was encrypted. Okay, so there's quite a lot of entities and algorithms here. Remember that these 2 master keys, public and secret, there's an identity, then there's a decryption key per identity, and as usual, messages and ciphertext. Let's now consider security, and the adversary's task will be to figure out something about the message given the ciphertext. So of course the adversary knows the master public key because everyone does. And let's say it knows what is the target identity for the encryption. And now it's given a ciphertext. The ciphertext encrypts and for that target identity a certain message M. And the adversary, you can think, is trying to figure out what this M is. So at its first cut, intuitively, security says that the adversary should have a hard time doing that. It can't figure out the message M encrypted to this identity, even given all this stuff. But actually, there's a little bit more to it. Now, looking at this, we know that the secret key associated to I, the one that will be generated here, is of course something we cannot provide the adversary. Otherwise, this would be trivialized. It could just decrypt this ciphertext and get the message. But what about other secret keys? Well, the definition says that if the adversary has or obtains the secret key corresponding to identities which are different from this target one, it should not help it in its task of recovering this message. So in fact, this is a much greater capability than we saw earlier, which is that the adversary can get the secret key for any identity different from the one that it's trying to attack here. Okay, and now we'll formalize that, and as usual, the formalization takes a sort of IND CPA type perspective in which you're not talking about the ability of an adversary to recover the message, but rather to distinguish whether a left or right message has been encrypted. And it'll take into account this notion of obtaining keys for other identities. So we fix our IBE scheme with its 4 algorithms and an adversary, and we're going to define a game. We'll again call it IND-CPA, and the subscript, however, tells us that we're talking about an IBE scheme. So let's start by looking at the initialize part, where parameter generation is run to get the master, public, and secret keys, and these are viewed as fixed for the rest of the game. The return statement here means the adversary is given the master public key, and this here is a random challenge bit. For the moment, ignore these over here. We start by looking at this procedure. IND-CPA, as usual, provides a left or right oracle. The adversary supplies 2 messages. One of them is encrypted. It has to guess which. The new element is that there's also an identity. The adversary says, I want to encrypt to this identity, and here are my 2 messages. Of course, they have to be of equal length. The game will encrypt M sub B, the message either M0 or 0 or 1, indicated by this bit, for this identity, create a ciphertext and give back that ciphertext to the adversary. And of course, encryption is a randomized operation, and the coins are chosen by this algorithm inside this execution. And then the adversary has to eventually output a bit B prime and wins if guess is a correct guess as to the challenge bit B. And its advantage will be twice the probability the game returns true, meaning twice the probability B equals B prime minus 1, which is the guessing correct probability scaled away from 1/2. These LR queries, the adversary can make as many as it wants. It can make them for many different identities and can reuse identities as much as it wants. Okay, now we get to that extra capability, which is that it's entitled also to decryption keys, but not to the decryption keys corresponding to what are called challenge identities, meaning ones that appear here. When it wants a decryption key, it can take any identity, go to this expose oracle and say, please give me the corresponding decryption key. The oracle will run key generation, that's the algorithm prescribed by the scheme, which has a function of the master secret key generated here, and the identity generates the secret key which allows decryption under this identity. And the adversary simply gets that key back. Now what we have to do is just make sure that no trivial break is possible by ensuring that the keys that are provided are not the ones for these challenge identities. To do that, we maintain 2 sets, the set of challenge identities and the set of exposed identities, and the game just makes sure they're disjoint. So whenever you call LR, if that identity has already been exposed, then the oracle will say, no, I'm not going to give you the ciphertext. Otherwise, it will record this as a challenge identity by inclusion in this set. Correspondingly, when you call expose, it will say, if this is a challenge identity, I'm not going to give you the secret key, but otherwise I will include it in the set of challenge identities. And with that, the definition becomes both strong and non-trivial. All right. So now we know what an IBE scheme is. We know what we're looking for in terms of security. So let's go ahead and build this. Well, where would we start? Well, we've studied a lot of number theory. We have RSA and discrete logs and elliptic curves and so forth. And indeed, over time, people looked for ways to use all these tools, which had been so successful for public key cryptography, to also create identity-based cryptography, and somehow never found a way. And indeed, you can sort of think about this a little. Like, suppose you try to use RSA. How would you start? Maybe I would set the master public key to be an RSA public key and the master secret key to be an RSA secret key. But then what is the secret decryption key corresponding to an identity. How do I encrypt for an identity and decrypt under that? And it's tough. It's just not clear how this is going to happen. And indeed, nothing like this particularly seems to work. So, and that's where pairings come in. These pairings or bilinear maps were present in mathematics. They can be built from the Weil and Tate pairings of elliptic curves, and they were imported into cryptography with this sort of first spectacular application of giving us identity-based encryption, and then followed by a whole bunch of usages to the point where now they're a common tool. So we discussed this a little in our studies of computational number theory and signatures, but let's recall that a pairing is a map or function with two inputs and one output. The inputs are both from a group G, and the output is another group called the target group and denoted G sub T. The groups both have the same order, which is assumed to be a prime number. Now, what does it mean for this map to be a pairing or to be bilinear? It means that when you take a generator of the first group, the following are true. If you apply the map to G to the X and G to the Y, what you get is its application to G and G raised to the power XY. Right? So you take G to the X, G to the Y, go to the target group, and that's the same as having gone in this way. And then a non-triviality condition, which precludes the map sending everything to the identity element, which would make this trivially true, is that E of G and G is actually a generator of the target group. Now, this enables a lot of algebraic manipulations. In particular, exponents can be moved around wherever you want. So for example, you can move the X over here and the Y over here. You can put both X and Y here and so forth, and it's all the same. So a bilinear map by itself is an algebraic object, but to use it for cryptography, we need some associated problem that we can conjecture realistically to be computationally hard, and then we can base security on it. We can use conventional problems. You could talk of computational Diffie-Hellman, let's say, in the first group. But for IBE, we need something else called the bilinear Diffie-Hellman problem. So having fixed the bilinear map, and hence also the groups, and fixed a generator, this problem is as follows. We recall first that in the computational Diffie-Hellman problem, you're given G to the A and G to the B, and you have to guess G to the power A times B. Here you start out a little bit the same. You're also given G to the A, G to the B, but you're also given a third one of the same form, G to the C, where all f, A, B, and C are random exponents. And all of this is in the first group. G is a generator of the first group. What you have to figure out to win is the result of the pairing applied to G and G. That's a public known quantity, but it has to be raised to the product of all the three exponents. So you multiply A, B, C, and you have to compute this quantity. And whatever cryptanalytic effort has been put in so far says that we are capable of building groups and pairings where this seems to be a hard problem for an adversary to solve. Okay. The advantage, of course, is the probability that the game returns true when run with the adversary. And there are various mathematical methods out there to build these pairings. But it's not easy. So the groups here are not as simple as ones we've seen in other parts of number theory we've studied, nor are these functions. And it would take a significant amount of mathematical background and effort to describe even what these maps are like. However, another way you can look at them, if you like, is to look at implementation. So there are various libraries out there, like the pairing-based cryptography library, which is a free C library and allows you to implement pairing-based cryptography with reasonable running times. So we now have the tools we need. We have our goal, IBE. We know what it means for it to be secure, and we know we want to use pairings to achieve it. So let's try to write down a scheme. So there's going to be quite a lot of things involved. Nonetheless, the basic idea is really quite simple and neat. So hopefully that will emerge from this. So we have our bilinear map or pairing from G cross tree to GT. We fix a generator of the first group. We recall that the prime P is the order of both groups. And we recall that I will denote the identity of the recipient, M is the message. We will have a hash function whose range is the first group. And we'll also have another function whose domain is the target group and range is the length of the message we want to encrypt. Okay, so IBE requires these 4 algorithms. The first thing we have to ask is, what are the parameters? What are the master secret and public keys? Well, this is quite simple. The master secret key is a random exponent and the master public key is G to that power. So now everybody has this G to the MSK. Let's now look at how you would encrypt. I have the master public key and I have some identity I that's the target and some message M I want to encrypt. Just as we saw for public key encryption, where we formalize the notion of key encapsulation mechanisms or KEMs, it often works by creating and communicating a secret key and then symmetrically encrypting the message with that. And it's the same kind of paradigm here, although we're not making it explicit the way we did there. But we can see here that a certain key K is created by the encryption algorithm, right? And then you just apply your hash function G to the key and XOR the message, and that goes into the ciphertext. So the crucial element then is K, because once you have that, you can decrypt. So let's see how K is created. You take the master public key, then you take the hash of the identity and raise it to a random power. And those two things, which are both elements in the first group, you pair. And that's your K. In the ciphertext, you put this W, and you also put G to the same power as you have here, so that some function of that R is available for decryption. Okay. Now we have to ask ourselves, not just how we decrypt, but what sort of key can be created associated to this identity that would allow that decryption to happen. So the trick is here, it's quite simple. You take this hash of the identity, the same thing as here, and you raise it to the power of the master secret key. Remember that the entity generating these decryption keys knows the master secret key. So it can perform this task and it returns that as the secret key. Now, we turn to how do you decrypt this ciphertext once you have the secret key which is created through this formula. And what it will try to do is recover this key K over here. And we will call that value L here. And the claim is that if you apply the pairing to this here, which is G to the R, and to the secret key created here, you will actually recover this value here. If we believe that, then applying the hash function G to L and adding W will of course recover the message. Okay? So the main thing is, why are K and L the same? And that is simply true by the magic of pairings. So, and we can work through that algebra quite easily. So by definition, L is the E of R and the secret key. Okay. According to the encryption algorithm, R is G to the power little r. That's how it was chosen here. And according to the description of the key generation algorithm, the secret key is the hashed identity raised to the power of the master secret key. Now, this hashed identity mathematically is an element in the first group. So I can write it as G to some power, since G generates the group. I don't need to ask something like, how do I know what power it is? Because this is just doing some math. Nobody is doing this algorithmically. But mathematically, I can write this as G to the I, and now I have G to the I times MSK up there. And now we use the bilinear magic. What that says is that all these exponents can just be shunted outside. So it looks like this. And in the middle I have E and G and G. And now I use it again. And when I use it again, what I can do is I can move exponents back in, but in different places. As long as the product of the exponents stays the same, it's all fine. So I can now put the MSK here and the other two things here. And since the three exponents are the same, this is all okay. But repositioning it like that shows us a quite different interpretation. G to the power MSK is actually the master public key. And since G to the power I is the hash of the identity, this is the hashed identity raised to the rth power. But now we see that we've recovered what's here. So we've recovered the key created by the encryption, right? So this K and this L will be the same, and the rest is quite simple. What have we done through this yellow box? We've proved the correct decryption requirement. So we've shown that if you have some identity and some message and generate the secret key correctly for that identity, and then if you produce a ciphertext by encrypting towards that identity a message M and decrypt under this secret key, you will indeed recover the message. Okay. So here, in summary, then it takes some time maybe to work through the details and play with the math, but we've seen how the magic of pairings lends itself quite elegantly to the creation of an identity-based encryption scheme. We're not going to go into details of the security aspects of the scheme, but there is a result proven saying that in the random oracle model, this scheme does satisfy the IND-CPA definition that we gave. Let's instead turn a little bit to what IBE gives us or perhaps doesn't give us relative to things like public key cryptography, because that's kind of interesting from the application perspective. So the benefit of IBE is that when the sender encrypts something, it doesn't need a certificate for the receiver or a public key for the receiver. It just needs an identity like an email address. And that makes the key management aspects simpler. Now, a feature, however, of IBE that one mustn't forget is that the receiver needs a decryption key, and that decryption key is generated by some trusted entity. That trusted entity uses its master secret key. As a function of that and the identity of the receiver, it generates a decryption key for the receiver and sends it to the receiver. So the result is that this trusted authority can actually decrypt all ciphertext for all identities, right? And it's interesting that how you view that depends on your persuasion or perspective. If certain organizations, for example, view this as a feature, they like the fact that they can decrypt, let's say, all the communications of their employees when they themselves function as a trusted authority for their employees' IBE system. But other ways of viewing this would be quite opposed to that perspective. This is creating a kind of a big brother setting in which there's some entity that can decrypt everything. This is not true in public key cryptography. The certificate authority there does not have the secret key and does not have the ability to decrypt things that the holder of the public key receives. There are other questions with regard to IBE as well, is a kind of a orthogonal or to the improved or easier key management, which is that it isn't just a question of whether the trusted authority is trusted or can be trusted to not misuse its power that it has through that master secret key. What if the server storing it was compromised, and then suddenly you have an adversary who's capable of decrypting all past and future ciphertext encrypted to all identities in the system? Again, in public key cryptography, if you compromise the certificate authority, you can create difficulties with regard to authentication, and there will be a lot of revocation that needs to happen, but you're not going to be able to decrypt messages that have been, ciphertexts that have been created before. Another challenge with IBE is how do you actually send the secret key from the trusted authority to the receiver? If that's not done over a secure channel, the adversary simply comes into possession of it. So there seems to be an implicit assumption of a secure channel from the trusted authority to the receiver. And it's not always clear how to realize that. And finally, revocation can be a challenge, because if you need to revoke a public key, you can always just do that, put it on the CRL, and the entity can get themselves a new public key. But how do you revoke an email address? Someone doesn't necessarily want to get themselves a new email address. So all these are interesting questions to explore and issues to be aware of. But meanwhile, IBE is seeing usage. Voltage is a company since acquired by Hewlett-Packard that has IBE-based products, and there are several more such things out there.